Hi, welcome to our third training session, where we will demonstrate how we can easily design, code, and debug LPC2148-based embedded system, which will drive 16x2 LCD module. Any embedded system project involves three important steps. The first step, we select embedded C as our programming language. The second step, LPC2148-based evaluation board. And the last step involves procuring 16x2 LCD display module. Programs written in C are readable and easy to debug. To debug embedded C program on the PC, we use a simulator. We use a Jaguar debugger to download and test the program running on the target hardware. Let us have a bird's eye view of our demonstration board. The demo board comes with LPC2148 processor. The first 8 general-purpose I/O pins are connected to header 1 from P0.0 to P0.7. Header 2 terminates 8 more pins from P0.8 to 15. Header 3 terminates P0.16 to 23. 16 MHz crystal. 5 volts to 3.3 volt regulator. The reset switch. ARM 20-pin header for downloading software using Jaguar debugger. Computer can only process binary numbers, but binary numbers, on their own, does not represent printable characters. Hence ASCII tables are used to map binary numbers to printable characters. LPC2148 communicates with LCD module by sending 8-bit ASCII data through header 1 and 3 control bits through header 2. The 3 control bits are register select, read write and enable. The 3 control pins configures the LCD controller to operate either in a command mode or data mode. LCD controller accepts 8-bit binary data and maps this binary numbers to display printable character. The LCD controller can display 32 ASCII characters in 2 rows, with 16 character on each row. Before we actually code, we will use a simple flow chart to visualize the steps required to implement LCD driver. On reset, the processor program counter R15 is set to 0. The compiler provided startup code is executed, and the program jumps to main routine. In the main routine, we need to initialize general purpose I/O. Hence the first function call to initialize LPC. We then need to define a general purpose memory pointer named message pointer to point to any message array. We need the second function, initialize LCD, which uses the message pointer to configure the LCD module. We need the third function, show message, to display our message on the LCD display. Hence in the first function call, initialize LPC, we set the port direction of first 16 bits to be output. Please note, the first 8 bits of our general purpose I/O will be used to output data to the LCD controller, while 3 pins from P0.8 to P0.15 will be used to control the LCD operation. The 3 bits will be register select, read write, and enable. In the second function, we will configure LCD to operate as an 8-bit module. This would mean the data bus is 8-bit wide. To write a command, we first need to access the command. This is possible by referencing our message pointer to the command table. When register select is low and the data bus is loaded with command data, then the LCD module will get configured. When we need to show message on the LCD display, we will be writing ASCII data to the data register of the LCD controller. This will require us to set register select bit high, then load the data bus with the first display character, and then toggle enable pin. To load the display character, On the general purpose I/O port, we use the same memory pointer, and reference it to the message table, and write a 32-bit value, to port 0. Let us try to understand the working of pointers. The first step is to configure the LCD controller by setting the RS bit low. The memory pointer points to the command table and reads the command until it hits a null character. The next step is to display message. This can be done by setting RS bit high. The memory pointer now points to message table. The pointer reads the message table until it hits a null character. So a simple while loop, a memory pointer, and toggle of register select bit is what we need to write driver for LCD controller. Let us start coding as per the flow chart. The first step is to define a character pointer named message pointer. All C program starts from main. As we all know, on power on reset, general purpose I/O port pins are all input. Hence the first function call is to initialize general purpose I/O port pins. The second function call is to configure the LCD controller. We then enter an unending while loop. Here we will display our message on the LCD display. On reset, all ARM7 registers are set to 0. This includes the general purpose I/O ports also. The I/O pin select and I/O direction registers are also reset. Hence the first step is to configure required number of port pins as output. We will be needing 16 I/O pins, 8 for driving LCD controller's data bus, and 3 more pins for handshake control. The bits will be register select bit, the read-write bit, and the enable bit. The enable bit strobes 8-bit I/O data into selected register. We will configure the LCD module as 8-bit data interface with 2 lines of display. The first step is to clear RS bit if it's set. We create an character array and initialize with command codes and terminate it with a null character. Our message pointer is initialized to the first location of the command table. We go on writing the commands to the LCD controller till the message pointer reads null. The first command 38 initialize the LCD module to work in 8-bit data bus mode. The remaining commands clears the display and homes the cursor. We toggle the enable bit high and low to transfer data to LCD controller. We create an character array sign on filled with message to be displayed. By setting RS bit high, we configure LCD controller to accept 8-bit data as ASCII characters. The message pointer is initialized to sign on array. Sign on data is transferred by toggling enable pin. The while loop breaks when the memory pointer return a null character. Okay, that's it for this LCD session.